Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and in this video we're going to talk about AC equivalent circuits. Okay, let's talk about Thevenin and Norton equivalent circuits for AC systems where we have a fixed value for omega. The process is going to be very similar to that we followed when we were doing resistive circuits with only resistors. Basic process is going to be find the open circuit voltage, VOC, find the short circuit current, I short circuit, and then we know that Z Thevenin is equal to VOC over I short circuit. Now VOC is going to be equal to V Thevenin, and I short circuit is equal to I Norton. So this is how we're going to find the equivalent circuits. What I'd like to do is we'll go through the process and then we'll talk about what that Thevenin's impedance means. Okay, so here's a circuit similar to many circuits we've done before, and we're given a value for Vn, and your assignment is to find the Thevenin and the Norton equivalents at the output nodes for this circuit with this input, and I'll give you and the values shown. Okay, so let's do that. Let's go ahead. We could do mesh or nodal analysis. I'm going to do nodal analysis because that's what I've been enjoying lately. You could do it either way. I'm going to call this node V. This node over here is Vn, and we're looking for VOC. Okay, VOC is this node right here. It is what is also labeled V out. And then our ground, of course, which we don't usually write in anymore, is down at the bottom. So I have to write two nodal equations, or three if we consider this one here. Of course, that equation is trivial. It's Vn is equal to whatever Vn happened to be. I think it was sine of 90t. 5 sine of 1000t, sorry. We'll deal with that later. And then let's write our equations. So we get the current going from here to here, V minus Vn over 2000, V minus 0 over 2000, V minus V out over 1000. So V minus Vn over 2000, or 2 times 10 to the third, whatever you want to write, plus V minus 0 over 2000, plus V minus VOC over 1000 is equal to 0. So that's our first equation. The second equation we're going to write at this node, okay, and we'll have the current leaving, VOC minus V over 1000, plus VOC minus 0 over this impedance, which is 1 over SC. Or in our case, it's going to be 1 over J omega C. So let's go ahead and write that VOC minus V over 1000 plus VOC minus 0 over 1 over, you can either write SC or J omega C. I'll just write SC right now. We'll substitute J omega in a minute. Is equal to 0. I usually do this because I have it in my head that the impedance is 1 over SC, and then I just substitute J omega for S. Okay, so those are our two equations. We now have two equations, two unknowns because we know what Vn is. We also know what SC is. I guess I could have written in C. Oops. Let's go ahead and write in C, which is 10 times 10 to the minus 6. It's kind of messy, but you see the point. Okay, so there's our two equations. Vn is a known. I'll show you what to do with that on the next slide. And everything else is known. And of course, omega, we're going to plug in S is equal to J omega. And omega is known. So I've got, on the next slide, I've got these equations rewritten. Okay, so Vn is 5 at an angle of minus 90 degrees, right? Let's go back and see what Vn was. Vn was 5 sine of 1000t. So let me just write that down. Vn of t is equal to 5 sine of 1,000 t volts. So the amplitude of that is going to be 5, okay? And because I put sine here, we have to account to convert it to cosine to have it in phasor form. So that's going to be minus 90 degrees. And of course, omega is equal to 1,000. So we take the equations from the previous slide, plug in Vn, plug in omega, and that we have these exact equations I have shown. Okay, now to solve for VOC, I want you to think back to what we were doing when we were doing circuits with only resistors. Normally what you would do at this point is you'd write a matrix equation, right? So we'll have something, and V and VOC will be equal to something, okay? So I want you to put in these values to get those equations in matrix form. Okay, so when you simplify those equations, actually, I didn't do a lot of simplifying, but I did a little bit. You end up with this matrix form. Okay, so that is 4 over 2,000 V. Okay, 4 over 2,000 times V minus 1 over 1,000 times VOC is equal to 5 at an angle of minus 90 over 2,000. The second equation goes in to be minus 1 over 1,000 V, and then we have a complex impedance or a complex number here, 1 over 1,000 plus 0.01 J times VOC will be equal to 0. Now notice I went ahead and mixed decimal values and fractional values. Whichever you want to do is fine. I usually go ahead once I have this and plug it into MATLAB. You can do that for your homework to check your answers. If you need to use a calculator, most calculators don't solve complex complex systems of matrix equations. So you would have to go ahead and do that calculation yourself. But on a test, I might very well ask you to fill out or complete missing portions of this matrix with the fill in the blank or multiple choice. So when I solve this, I get a value for V, which I don't care about, so I didn't bother to write it down. And we end up with a VOC is equal to this value, and of course the units is volts. Okay, and I can write it in, I want to write it in polar notation, so I can write the time signal. And we have VOC as a function of time will be equal to the magnitude, cosine omega, which is 1,000 times t, plus that angle, which is minus 177 and a little bit. And this is the Thevenin voltage. And notice that we've written it as a function of time because it is a function of time. The next thing we need to do is find the short circuit current. So the first step is to short out the load. In this case, we're looking at the equivalent circuit seen by the 10 microfarad capacitor. So that's what we're going to short out. Okay. And when we short that circuit out, all the current is going to go here, not here. And so what that means is this is not, it is effectively not there. So that gives us a very nice simple equation. We can, and the current, let's go ahead and define I short circuit before I forget. I short circuit is this current. So we can go ahead and do our nodal analysis. If I use nodal analysis for VOC, I usually use it for I short circuit, and same thing for mesh. My equations are simple, so my mind is already working in the right direction. Okay, so this node will be, I'll call it V. This node, of course, is Vn. This node down here is ground. And so we have a very simple equation to write. So we have V minus Vn over 2,000 plus V minus 0 over 2,000 plus V minus 0 over 1,000. So V minus Vn over 2,000 plus V minus 0 over 2,000 plus V minus 0 over 1,000 equals 0. And Vn is known. And we solve for V. But V is not what we were looking for. We were looking for the short circuit current. But the short circuit current is this current, right? And that's going to be the same as the current through that 1K ohm resistor in this direction, right? So now we know that I short circuit is equal to V minus 0 over 1,000. Okay, so there's our basic equations. Here they are written down again, and I've stepped through some of the steps of solving. Here's our equation from the previous slide. I just factored out all the coefficients for V on the left, move V into the right, and I get a value for V to be equal to a quarter Vn. And Vn, of course, remember, is 5 at an angle of minus 90 volts. Just like it was before. That was our given value. So I short circuit is going to be this value of V divided by 1,000, which will give us 5 over 4,000 at an angle of minus 90, okay, which gives us I short circuit in polar form. And then we can write that as a time-varying form. The magnitude, cosine omega is still 1,000 times T minus 90 degrees amps. And this is the Norton current. So we've done the first two steps. We found VOC. We found I short circuit. Now we need to find Z Thevenin. So Z Thevenin is just going to be equal to V open circuit over I short circuit. And I don't recall those values, but I have them on the next slide. Okay, so VOC was 0.1248 at an angle of minus 177.1376. Notice I'm keeping all my values. I short circuit was 0.00125 at an angle of minus 90. I go ahead and do the division. I divide the magnitude by the denominator magnitude to get 99.84, and I subtract the denominator angle from the numerator angle, and I end up with minus 87.1376 degrees. Okay, now at this point, we want to know what the Thevenin equivalent impedance is, and of course that is this value ZT. Okay, but what is that going to be in terms of resistors, capacitors, and inductors? So let's figure that out. So here's our value. ZT is equal to 4.9858 at minus J 99.7154. Okay, and the units for that is ohms, for those of you who like to keep track of your units. And so we just need to look and see that the resistance part of ZT is going to be this value right here. So if we look at this impedance, we know that it is a resistor in series with either an inductor or a capacitor. Okay, think about what the impedances are and how we add numbers in series. So this will be the resistor. Okay, capacitors and inductors don't have resistance, so this is a pure resistor. Okay, and in general, we usually define Z of T to be equal to R resistor plus or minus J times X. Okay, and we leave it as an X because that's actually a term that's often used in the power industry. And so we know that our imaginary part is minus J 99.7154. If it were an inductor, it would be a positive value, right? Because the impedance of an inductor is J times omega times L, which would be J times a positive number. A capacitor is going to be 1 over J omega C. Okay, the J in the denominator becomes a minus J in the numerator. And so you'd end up with a negative value. So that's the rule, if you need to remember it. If this is positive, it's an inductor. If it's negative, it is a capacitor. Okay, sure enough. So let's figure out what that capacitor is. We know that 1 over J omega C is the impedance of a capacitor. I just went ahead here and brought that J up into the numerator. You can check your math to make sure that you believe that. We're going to set that equal to the value we have here. The reactance is what it's called. And then we're going to solve this equation that I just circled for C. When we solve that and plug in for omega, right? Omega is known. And if I recall, it was 1,000. Let me double check. Somewhere here. 1,000. Just being sure. And you should double check yourself, of course, as well. Sorry. So this is to be omega's 1,000 radians per second. Right there it is, right, written below. Okay, so that is our value when we solve, plug in omega, solve for C, we end up with about 10 microfarads. Okay, so if we drew this as a circuit, let's see what we would have. We'd have VOC of T, and that has a value. And then we'd have a resistor, which is the an R, and then we have a capacitor for our case, which was C. Okay, and then this is, of course, the equivalent circuit. This is the Thevenin equivalent circuit. We can also draw the Norton equivalent circuit. It's going to be IN of T. I guess I should have put a T here just to be clear. So it's VT of T, which is VOC of T, and IN of T, which is I short circuit of T. And then we're going to have in parallel a resistor, and in parallel a resistor with a capacitor. And that's the Norton equivalent circuit. So in general, what you're going to have here is this is going to be ZT, whatever that is. And of course, this will be ZN. And recall, ZT is equal to ZN. I didn't tell you that this time, but we had that for resistance circuits. And there's our two equivalent circuits. And you should know how to draw those. Okay, and you should be able to solve for R and C. So the value for C we got was about 10 microfarad. Write it down. R was about 4, almost 5. So you would just write those down. Now, the other thing we did when we talked about resistance circuits is we asked for what load impedance do we need? So like if we put it here, what load impedance, let me put a Z. Let me just sketch it in for you. So this is where the load would be added in both cases. And it's an impedance, so I'm calling it Z and drawing a box instead of drawing a, and I'll write load just so it's clear. Drawing it a box just so that you can know that it's not, you don't know what it is exactly. So when we ask, in the case of circuits that have capacitors and inductors, we now have to look at the load impedance for maximum power transfer just a little bit differently. Okay, so in our DC circuits that were purely resistive, right, the load resistance was equal to the Thevenin resistance for maximum power transfer. Hopefully you remember that from before. So that means that our load for maximum power transfer is going to be equal to Z Thevenins. But what about that imaginary part of Z Thevenins? It doesn't actually contribute to the power, but it is an added impedance, and it can we can have negative imaginary impedances. I know we can only have positive resistances, but we can have negative imaginary impedances. So if we go back to our value, we had 4.9858 plus minus J 99.7154. So what we want to do is choose for our load. We actually want to choose a positive value here. so that it goes away. So when we add the two together, we will end up with just a resistive part. So what we want to have is the Z load, again for maximum power transfer, will be equal to the complex conjugate of Z Thevenins. Okay, so Z load max, I'll just write max power transfer. It's going to be equal to Z Thevenin's complex conjugate. We put a star there. So what that means is we're going to set Z load equal to the positive value, 99.7154. Remember, I'm sorry, X load. X is what goes beside the J. So we're going to have J 99.7154 will be equal to J omega L. Of course, omega is known, and it is 1,000. Since that was given. And we solve, and we end up with an inductor of 99.7154 millihenries. Okay? And so that is the impedance for maximum power transfer. So if we drew that, well, let me just go back here for a moment. So that means, let me copy this and I will put it a little more orderly for you. Okay, so here's our value of ZT. So Z load for maximum power transfer will be equal to Z Thevenin complex conjugate, which will be equal to 4.9858 plus J 99.7154. And so that will be Z load max. Okay. Now, if we go ahead and go back to our circuit, let's look at the Z Thevenin. It works just the same for the Norton case. Okay, what we're going to end up with is the values we found previously for the resistor and the capacitor. Okay, I didn't write them down, but whatever they were. Okay, and then for the Z load, we're going to have, you can go ahead now and write in a resistor and an inductor. And that resistor value will still be R, and the inductor value will be what we found on the previous page. What was it, about 99 millihenries. Okay, so when we do this, this is for maximum power transfer. And so when we look at this and we go ahead and write the mesh equation, we'd have a current I. So we'd have minus VT plus I times R plus I times 1 over SC plus I times R plus I times SL. And when we plug in the values, the C and the L will both cancel, and we'll just have I, okay, minus VT plus I times 2R. Okay, and from there you can solve for the maximum power transfer, etc. So those are some things to think about at home. We'll address them a little bit more later as well. But now what we've done is we have found the Thevenin and Norton impedance for an example circuit, and we've talked about what impedance load we need for maximum power transfer. Thanks for watching. I hope you found this video helpful.